Hi everyone, I'm Daniel Bergqvist. I'm a solutions engineer on the cloud platform team. So I'm here today to speak to you about containers and Kubernetes. And if you think that you want to learn more about containers and Kubernetes and you want to learn it straight from the horse's mouth, you should go to the silver stage at 12:45. Because then Eric Brewer, who's a senior VP at Google, will speak about containers. He's also a professor at UC Berkeley, and he's basically a legend within distributed computing. He's the man behind the CAP theorem, for instance. So don't miss that for the world. I won't. So how many of you are familiar with containers? Show of hands. Okay, if you want. Kubernetes? A little bit? Good. So let's start with talking about why I'm excited about containers and Kubernetes and so forth. So personally, I think that when the cloud came about, it was all about for the first time we will see true portability. There will be no vendor lock-in. You will be able to manage to move workloads between Amazon and Google and Microsoft and so forth. But that promise didn't really happen. It's still really hard to move a virtual machine from Amazon to Google or vice versa. But I think that containers is really the solution to that. It's truly portable. It's easy to move workloads on-premise to the cloud, back to on-premise to a different cloud provider. And I think that's great. That's great for everyone. So now everybody can compete on providing a good service and not competing by locking customers in. Also, as an engineer, I think containers are fantastic because it uses resources in a very sane way. The resource utilization is really, really beautiful if you compare it with managed VMs or with virtual machines, sorry. So it basically lets you focus on your code and you don't have to worry about, instead of focusing on the machines they run on or the network and etc. So, in the cloud today, we have a lot of options. We have a continuum of options between the highest level of flexibility and the highest level of agility. So, at one end of the spectrum, you have virtual machines. That's basically raw power that you rent from a cloud provider or you run it on-premise. But you get a lot of flexibility with that, but on the other hand, you still have to do a lot of DevOps. So you still have to manage the network. You still have to spin up instances. You still have to scale your clusters, etc., etc. On the other part of the spectrum, you have App Engine, platform as a service type of services that are super elastic so that you can scale from 0 to millions of requests in seconds. But the drawback with App Engine, or the limitations with App Engine, is that it runs in a sandbox. So whatever it supports, that's what you have to play with. If you need support for image magic because you're doing image rendering, that won't be supported. So then you have to do that somewhere else. But as long as you can live in that container or in that sandbox, then that's a brilliant service. So, but what we're trying to do with containers is to bring virtual machines, infrastructure as a service, and platform as a service together, so that you get the best of both worlds. So, I don't know how much you know about containers, but I'm going to spend a few minutes explaining what a container is. So, if you're familiar with hosting multiple applications on a single machine, you know what a pain that can be. There's no isolation between applications, which for one can be a huge security issue. Additionally, you run into problems when applications need different libraries or different versions of a library or even different versions of an operating system. So virtual machines try to solve this problem. So it provides isolation, but each application gets a copy of the kernel and their own library, so conflicts aren't really an issue. But it's not really efficient use of resources. If all your apps use the same kernel, why do you need 4 copies of it? So, containers, a much nicer resource utilization. So the kernel is shared by all applications. So that means that if some of the application doesn't do anything, one process could utilize 100% of the CPU. But each application gets its own libraries and runs isolated from other applications. And basically, 2 containers could share also the same set of libraries if they need the same set of libraries. Yeah, and that's what we see here. So this is a more concrete Docker example. So what we're running here is like PHP and an Apache web server. We're running memcached, MySQL, and then the Docker engine that coordinates everything. So let's say that this is a simple guestbook applications. There are 3 containers, and they live all on the same host machine. The kernel is shared between all the containers, and where possible, like for instance the PHP and the memcache can also share the common libraries. Whereas MySQL is built on a different set of libraries, so that will contain its own libraries. So I think it's really good. I mean, at Google we really like that people are starting to pick up containers. We've been running containers for years at Google, like, I don't know, 10 years maybe. Everything at Google runs in a container. If you rent a virtual machine from us, that virtual machine is actually running in a container. And just to give you a number, we spin up 2 billion containers each week at Google. So we have some experience on how to do that. Of course, all our other services are also running in containers. So, why is containers so great? The performance. So, containers start up really quickly. If your system needs to provision and then initialize a VM to scale up, I mean, a virtual machine takes like a minute maybe, whereas containers, you can spin up containers in seconds. So also, since the kernel is shared, you can put more application on one single host. And because you aren't dealing with like sharing the kernel as you do with a virtual machine, you get like native CPU performance when running with Docker containers. So, also, containers are self-contained. They have all of the dependencies included, so you know that every time you deploy a container, you're getting a node with the same libraries, application code, and capabilities. Even if one of your dependent libraries has a version revisioned, even if the package manager is down, your container starts up with exactly the same file system every time. Quality of service. So different apps need different guarantees, different SLAs. So containers allow you to specify what resources your application actually needs and ensure that those resources are available for your containers. Because of the way containers are specified and created, you get a much better picture of what resources each container uses. And of course, as I said earlier, the one I think is one of the biggest points for containers, the portability. They can run anywhere. You can run them on your own hardware. You can run them in the cloud, public or private. You can run them on the same container. You can run the same container in multiple clouds. Run them on your dev box. Every possible environment you need. So, containers solve a lot of problems with VMs, and they are fundamentally a different way of deploying and managing your applications. Container gives you a lot of benefits. Mostly, though, they move from a late binding of application with dependencies to an early binding. So instead, with early binding, I mean that like you have to manage that when you build the container, not when you deploy it. So, container sounds awesome, but a lot of people I've talked to are worried about managing them, that should be harder than managing like virtual machines. But here at Google, we've been using virtual machines in the industry for years, or the industry has been using virtual machines for years, and there are some great tools for handling virtual machines. So Kubernetes is Google's solution for managing, running, and monitoring applications made up of multiple containers. So Kubernetes is basically a product that was invented at Google that we then open sourced, and there is a variety of big industry players behind Kubernetes. So Kubernetes is a very sophisticated and powerful system, but you don't really need to understand how it's built to use it. You just need to know how your architecture maps to Kubernetes concepts. So let's go through. This is like a simple guestbook app. We have some PHP code running on an Apache server. We have a MySQL database, and we have memcached. So some of the challenges here would be like, how does the PHP code find the cache process, for instance? What happens if one of the machines goes down? How can I run this environment in like a QA dev production environment? And how do I scale? So first, enter Kubernetes. The name may seem a little bit odd, but it comes from Greek, and it stands for Helmsman. So it's like you're the captain deciding where to go. Kubernetes is responsible for carrying out your orders and ensuring that everything stays on track. Kubernetes run Docker containers, but also Rocket containers, which is another container format. As I said earlier, can run anywhere. So when we built Kubernetes internally, we use our internal incarnation of Kubernetes is called Borg. So we've used what we learned from building Borg and taken the best parts from Borg and put them into Kubernetes. So I would say that although we're still running Borg internally, I think we would love to run Kubernetes instead. So, desired state. This is really the key concept in Kubernetes. It's a declarative configuration. So you basically describe how you want your ideal world to look. Like, okay, I would like X copies of this and Y copies of that. And then Kubernetes will help you to keep that desired state. And that lets you, of course, focus on your application. So the four primary concepts of Kubernetes is a pod, replication controller, a service, and labels. High level, this is like the core concepts of Kubernetes that helps us to retain this desired state. So let's start with pods. A pod is made up of one or more containers that are tightly coupled. So these are the smallest these are the smallest units of your cluster. So the containers in a pod cannot be deployed separately. They're always part of this pod. So containers in a pod, they share an IP address and a local host. So, and also they are ephemeral, so it should be possible for them to die and then be replaced by another pod. One common question is whether a web server and a database talks to one pod or two. So you can set up the system any way you want. If you want to scale the two independently, you should have one pod for your database and one pod for the web server. So not running them in the same pod, split them up so that you can scale them separately. A little bit like a microservice architecture. So in many applications, you like more than one instance of a pod. For example, you might want 4 front-end web servers. So replication controllers are responsible for maintaining your desired states. So let's say that like your desired state is 4 instances of the front-end pod. So it's very similar to a process supervisor, for instance. So let's go through the replication controller. So I don't see this slide. So here we have 6 pods. That's the desired state, and the current state is 6 pods. Then, boom, one of the machines is hit by lightning, is struck by lightning, maybe you say. So one of the machines is gone. So then all of a sudden we have a desired state of 6, but the current state is 4. We will then redistribute containers. So on the 3 nodes that are still up and running, we will deploy 2 new pods. Then the old machine comes back up again. And then all of a sudden we have a desired state of 6, but we have the current state is 8 pods. So then Kubernetes will remove 2 of the pods for us, so that we always keep this desired state. Like this. So, services. Services basically simplify accessing pods. It's for discoverability and load balancing. So if you have multiple instances of a pod, let's say that you have multiple instances of your memcache service, the service will act as a load balancer. So in all cases, the service gives a pod a virtual IP, a stable virtual IP. So the PHP code, for instance, always knows, it always can go to the service in order to find the memcache. So it doesn't matter if like it has 10 memcache instances running below the service or if it's 5. So just like with replication controllers, which pods are in a service is controlled with labels. So let's check out what a label is. So if you want to use like selectors to group your pod, you need labels. So labels are just arbitrary metadata attached to a pod, a replication controller or any other API object. This is basically the only grouping mechanism that you have in Kubernetes. It's purposely designed to be flexible. For example, all the pods in your app might be labeled with like app:guestbook. The nodes used for the test environment could then be labeled phase test, and you can label the front-end and back-end services according to their roles. So this is then how our guestbook application would map to the concepts that we've talked about here. You have the front-end instances, the front-end pods running. You have services for discoverability in front of the MySQL and the memcache service. So, what is Google Container Engine? That is basically, if you want to run a managed Kubernetes, then we do that for you. So it's fully managed. You get if you don't want to use the command line interface to manage your clusters, we will provide a web UI for you. We also provide a private container registry. So if you have private, or your company have private Docker images that you don't want to host like on the Docker site, you want to have them private, we have that for you. It's also integrated with cloud logging. So all our products at Cloud Platform actually share the same logging function. So you can see the state of all your applications running on Cloud Platform. So that was a really, really quick overview of what you can do with Kubernetes. And as I said earlier, if you want to hear this story from the horse's mouth, 12:45, the silver stage, Eric Brewer, VP of Infrastructure, Senior VP of Infrastructure at Google and Professor at UC Berkeley. Thanks for listening.